Okay, guys, let me try and make this as short as possible. I'm looking at DC machines, electrical trade theory, and we're just looking at revision before, right? Um, yes, here's the presentation. All right. Um, guys, what we need to understand about DC machines is that we've already spoken about AC machines, which use alternating current, live and neutral, as well as it also uses three-phase machines. Those are motors. We've already spoken about them. The construction is basically almost the same because you're going to have an armature rotating inside a magnetic field. Now, the thing is here, our magnetic field is mainly just your North Pole and South Pole in terms of magnets. So let's look at how it is basically going to be structured. You've got your North Pole there, and you've got your South Pole there, and then you've got the armatures, which are your conductors that are going to be rotating inside the magnetic field. Okay, we are going to explain. We are going to explain how they work. And then you're going to have the commutator and the motor itself rotating inside, which is connected via the armatures. You see, this the commutator is these segments there. You can see it's small segments that are split, and then you've got your battery, positive and negative, that is going to be put through what are those? Those are brushes. Then you've got a pole, which is your North Pole and your South Pole, and you've got a pole shoe. This part here is called the pole shoe. All right. The overall structure is called a yoke, as you can see there. The overall structure is just called the yoke, the outside of this. So this is how the DC pole motor is constructed. Well, if you go to your textbook, you're going to see where it says terminal box. You already know what a terminal box is. You're going to see the interpoles. They are very important because we are going to be, please take your textbooks and so that you can move along. I'm on page 121 right now. You've got main poles, brushes. We've already spoken about them. Yeah, so that is what we are going to be having as our DC machine. We are going to learn how they work. But what is important from this is that you've got brushes that are in contact with the armature, and the current goes through the brushes, and then the brushes distribute the current to the commutator, which is the segments that I'm referring to. So I'm gonna explain to you what those mean. I don't want this video to take more than 15 minutes. Now, let's look at the armature assembly. So in other words, we are talking about the armature. Now, the armature consists of, if you look at your textbook, because here I'm just referencing here, you can see the commutator bars, the commutator. Now, each side of a commutator is connected to a certain wire. This one is connected to a wire, that one is connected to a wire, just like that, to a set of wires. And then those wires go through, and then they come back to the other side of the commutator then. So this side at the back then will be where this wire is connected. It's gonna go through and then come back at that end there. So to complete a loop. So that when we supply our current through the brushes, when the brush is touching here, the other brush would be touching the same wire, but on the other side to complete a circuit, okay? To complete a circuit. But it's gonna make sense. So this is the armature. These are winding coils. So this is the shaft. This is the shaft, as well as that one outside there that appears at the front of our okay, at the front of our motor. Then we are going to have also the fans that are connected here, so that when the motor turns, the fan will also turn. You've got carbon brushes. Now, remember, I'm looking at your textbook now. Remember, the brushes have got springs, and look at how they are in contact. One is at the top, one is at the bottom, to allow for this connection of plus and minus on the same loop of wire. Hey, I hope that makes sense. But we are going to look at it. going further. So this is what an assembly is. So an assembly consists of a shaft, a fan, an armature, a commutator, carbon brushes, which are, yes, which are in the, and then the bearings. The bearings are also part of that. Right, now, let us look at this. Now, here's the loop. Here's the one commutator. Now, since we've got only one loop, we're going to have only one set of commutator winding. Only one set. Remember what I said here? I said, if there's only one loop, I wish I could make this in a different color. Let's try green. But I want you to at least understand what is happening here. So if this is connected like this, it's going to go through like that right up until the back end of this commutator, so that the brush is going to touch here and there at the back, the brushes, making a loop on this winding coil. All right, now, here it is, the simplest form. Now you've got your North Pole, the South Pole. I'm not gonna be very deep on this one, please. Now, you've got the current flowing. Look at from positive. It goes through the coil, comes back through to the commutator. Remember, the commutators are connected via brushes, which means the commutator will rotate inside the brushes. The brushes remain in one position. The commutator is the one that is connected with the what? With the wire. So these are permanent. This is a permanent contact, but the brushes are not permanent contact. Let me just check the textbook. Oh, yeah, look at how the textbook puts it on page number 123. Yes. So the commutators are permanent with the armature, while the brush contacts remains in one position, which means what turns here is the commutator as the okay. What turns first, obviously, is the armature inside, and then the commutator will also turn. Now, what is important here is that we want the current in this place to always be coming backwards, meaning the force will always be going upwards. When the current is going in that direction, the force is going down. So we can see a rotation there. So that's what the commutator will be doing. Just a minute. Just a minute. Okay, as we continue then, so the commutators are going to turn inside the magnetic field. Meaning that if this commutator side A has shifted to the side of B, the side of A will still experience the same current because it will be fed from the positive side of the brushes, which means this thing will continue to turn and turn and turn and turn. All right, but I want us to look at a video which is going to help us at least understand this a lot better. I'm just hoping that I'm not stealing people's material. There we are. Okay. I hope the sound is going to, we are going to get the sound.
In this video, we will logically understand the operation and construction of a commercial DC motor. In large DC motors,
Pardon me?
let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But If you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in two different ways: parallel or series. The result is two different kinds of DC motor constructions, a shunt and a series motor. The series wound motor has good starting torque, but its speed drops drastically with the load. The shunt motor has a low starting torque, but it is able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF. A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the rotor. At the starting of the motor, back EMF is too low, thus the armature current becomes too high, leading to the burnout of the rotor. Thus, a proper starting mechanism that controls the applied input voltage is necessary in large DC motors.
Okay. This is really good. It went even further to explain things that I'm going to be explaining to you. So at least you have an understanding now. So I hope you saw the operation. If you want to repeat that, you can just scroll backwards and then check that out. Right. So it spoke about back EMF. We're still going to come to that. Now let's look at something called armature reaction, because when the rotor rotates, so you can see here, this is the North Pole and the South Pole, and these are the coils. The coils, meaning that what you see here is the coils, and then when they start rotating, what's going to happen when they rotate? Now, when they rotate, they will form something like this. I'm not gonna explain again into deep details, guys. And two, what they will be looking for you here is the definition of this. Now, as you can see, guys, here, when this rotor starts to turn, you see that the magnetic field was straight. Now look at the magnetic field. Now let me just highlight this one in red. Look at the magnetic field now. Look at the magnetic field now. Look at them. It's no longer straight. So what is the armature reaction? It's the distortion of the main flux due to armature flux. It's the distortion. When something distorts, it means that it is actually losing the original shape. So this is the distortion. All right. Let's take it from here. So that is what we mean by Amateur reaction. All right. So as you can see there on page 124, they also show that amateur reaction. They also show that amateur reaction. Now, what I want you to know now is that the coils can be connected in 4 ways. It is separately excited, it is series, shunt, and compound. I hope you've learned from the video. We were talking about a series, a motor. We spoke about a shunt motor. Here we're going to talk about also a compound and a separately excited. Now, if you can draw this table and know it, it will be very helpful for you. Because for a separately excited, the motor is on its own. The motor is the motor, and then look at the winding that excites it, or the winding that that is used to. So there's the winding there that produces a magnetic field that's going to cause the motor to rotate. So that's what we mean by separately excited. How do we draw a series one? A series one, there's the winding, and then here is the motor. Now, the series is connected. The winding is connected in series with the armature. What happens on a shunt? You have the motor. Oh, please draw this thing much better than me. You have the motor, and then you've got the winding in what? In parallel. Now, the compound would be either a long shunt or a short shunt. I know you do study this in ETT, industrial electronics, so I'm not going to take a lot of time on these ones. We have a long shunt. Now, what is the character of a separately excited? How does it behave? Now, a separately excited motor, well, we know that it is used in smaller motors, and that's basically what it is used on. What is the characteristic curve? We don't have a characteristic curve on this one. We literally do not. And then when we move on to, and then the applications, which we on your textbook, there's no application that is mentioned. So I'm gonna leave this one here like this, right? And then we go to a self-excited motors, which in other words, the winding is connected directly to the motor. This one is separate. So we start with a shunt according to your textbook. It says a shunt is connected in parallel, operating the same voltage. So the voltage is constant in parallel, as you know. But what's going to happen to them? To the current. The currents are going to split in a shunt. Now, there's a mistake that they made there on that shunt, page 125, figure 6.7. They say IL is equal to IA is equal to I shunt. No, IL is equal to IA plus I shunt. IA plus I shunt. Now, what are the applications of this one? We say we use them for lathes and fan. Lathes, nama fan. Okay. What is happening? What is their character? What is their character? Their character is that they have got high starting torque. So you've got high torque as well as what? But their speed is constant. High torque, constant speed. Constant speed. Now, how is the character going to be? Remember, the speed is almost straight line. So you're gonna draw it like that. This is IA, and this is your speed. You can just write N, the speed. So it's almost constant. You can see it's almost constant. That will be the that would be the shunt character. What about the series? Now, guys, pardon me here. I also mix these things. This one has got a low torque, actually. Series has got low torque. The high torque is on the high torque is on series. So high torque on series, and if it has got high torque, meaning it can be used for armor lifts, forklifters, electric trains, which require high torque, nama forklift. Sharp. And then the characteristic curve is gonna go like that. Why like that? Because when the speed is high, the current is less. It's inversely proportional. Right, so that's how the characteristic curve is gonna look like. I want you to notice something, guys. I want you to notice something here. Here in series, IA is equal to IL, meaning the current is high. Now, the higher the current, do you remember what we were talking about when we're speaking about high current? High current simply means thicker conductors. As you can see on that pole shoe, you are going to have thick conductors. Those are conductors, armature conductors. They are going to be thicker conductors for the series. Why? Because bigger current is going to be circulating on those conductors. So that's why you need conductors to be thick. You can see those, they are thick conductors. But on a shunt, what is happening? The current is less. Why is it less? Because the current is dividing between armature and shunt, which means the current in the shunt is going to be less. Now, the less the conductor, it means now you're going to have smaller conductors. But the smaller the conductors means the many they're going to become. As you can see, the pole shoe there, it's got many but small conductors which are going to be connected around that pole shoe. So I hope you understand that part there. Then our compound, guys, you're going to have a long shunt and a short shunt. Please go through that. But what is important, again, the characteristic curve for a long shunt and a short shunt, it simply says that you're going to either have, okay, here's the level. If they are connected, they are either going to be differentially compounded, that's the curve, or level compounded, that would be the curve. That's how we are going to draw that. The others, obviously, there's a series, there's a cumulatively compounded, there's a level compounded, all of them on that figure 615, they are just showing us the different types, okay? Now, they already spoke about back EMF, guys, back EMF. Back EMF is the EMF that is formed. Why? As this thing is rotating inside the magnetic field, an EMF is induced. Although it is a motor is not supposed to generate EMF, but because it is cutting the magnetic field, that EMF will be produced. That EMF is called back EMF, very useful back EMF, because it will oppose the current that is flowing. So you can see the current is flowing in that direction, back EMF will flow in that direction. Which means if I could get, if there's no back EMF, the current is going to be very high. This one, this IL is going to be very high, or IA, current going to the armature will be very high. So I need this IB, I'm going to call it IB, back EMF, to reduce this this IA. Because if this IA is too high, it's going to bend the windings. If it's too high. Now, what am I going to do? Now, remember, so this one is to help this motor to regulate. Now, if this rotates, if this has not rotated yet, the IA is too high without a rotation. But as this rotates, because remember, it must cut. According to Faraday's law, it says when a conductor cuts a magnetic field. So when it starts rotating, that's when you're going to start getting the back EMF. Now, the more back EMF we get, the lesser and lesser the current IA, which is the starting current. Meaning that before the motor starts, you've got high IA, which means this motor is going to burn. You need to generate big EMF when this rotor does what? Starts turning, so that it will reduce. But before we start, we have a problem. We've got high armature current. What do we do? What are we going to do there? That's when we are going to have something called a phase place starter. Phase place starter. It may not look exactly the same way as the one that you are having on your textbook. This one is a series one. How does it work? Guys, they can ask you to draw this, so you need to know. Right, so as you can see, the current plus, let's follow this current here. I'm trying for this thing to make sense. Follow the current there. There we go. It is not connected, but it's going to be connected to those. And then complete the what? The circuit. You see? So in order for it to complete the circuit, as you can see here, it must touch on R1, then the circuit is complete, which means the motor will start to turn. Now, why does it have to start on R1? Remember, before the motor begins to turn, we say there's high what? IA. So if there's too much IA, what do we do? IA is equal to EMF over RA. If I can increase the resistance, I can reduce the armature current. So with the high resistance, I've got lesser what? Current. So look at this. I've got 1, 2, 3, 4, 5, 6 points at which I can place this arm. So when the arm is on position 1, it means the circuit is now connected, the current is flowing. But look at the resistance. The resistance is very high. Why is the resistance very high? Because the motor has not yet rotated. If the motor has not yet rotated, it means the current is too high. To reduce that too high current, I increase a lot of what? Resistors, or I put in my circuit a lot of resistors. As the resistors are too high, the current will drop. That's how I drop the starting what? Current. Now, as the motor begins to rotate, the back EMF is now created, making IA to be lesser, which means now as the motor rotates, I can move the arm to position 2, reducing the resistance. As the motor rotates, it's generating a greater IA until the motor rotates at full speed, which means the arm will now be on 6. I no longer need the resistances because now I'm going to be regulating using what? Back EMF. Back EMF is the one that's going to be countering the armature current without the need of resistors. So this is why we need a phase plate starter for a series motor or for a shunt motor. Replay that if you don't understand. Right, how do we change the rotation of a DC motor? Please, let's just go to a series. Here's the winding there. So if you want to change this, what do? Just swap the connections on the winding, or swap the connections here. What am I doing? It's either here, or you can take this connection, put it here, take that connection, put it there. But obviously, guys, you won't be having this connection anymore. Yeah, you see. So you either rotate by using the rotation of a motor or the rotation of the winding, but not both. So as you can see there on page 130, they are giving us all the examples of a long shunt, short shunt, series, and field motor. All right. Guys, I don't want to go through the operation of a DC generator. Please go to YouTube. Please. I don't have time. This is going to take longer than I thought. I do have a video, but I don't want this to be too long. All right. So also what the generator does, obviously, is the fact that it must rotate in order to give us what? Current. Please read through that. How to improve commutation. Now, what is commutation? Is the reverse of polarity to the external switch with every half of the rotation of the armature. The same way we were using commutation on DC, it's almost similar to this one again. Now, how do we improve commutation, guys? We are told on page 133 that you must increase the brush resistance. Please take note of that. You must shift the brushes. They also tell us that you must increase the field windings. Increase the field flux. You must use interpoles or use compensating windings. Please take note, maybe know 3 or 4 of those, which would be very important. Now, what else do we need to know in this chapter? Because I'm doing a summary. I don't know why I'm taking too long. There's also a separately excited generator. There's a self-excited generators, which are series, shunt, and compound generators. And then we can also reverse them. No, we don't reverse the rotation of a generator. Yes. So I want to see this, guys. Please, when I say draw a motor, let me just put this. I think this one is important. This is a series motor. Look at the current. IA is going into the motor. This is a motor because the motor needs current to rotate. But if this is supposed to be a generator, same thing. What is going to differ? The current is going outwards because the generator gives us current. So this is the difference between a motor and a generator. The current from a generator comes out while the current in a motor goes towards a motor. I want you to take note of that. Guys, let me hold it here. I have another video to make. I'm going to try and send it to you.